to the first lecture in mathematical methods of signal and image processing. So I'm very happy to be back actually in a lecture room, being able to see all the students that are here, seeing your faces and see whether there's a chance that you understand what I'm saying or just staring in blank faces, so I can adjust hopefully. And so as I said, this was planned as Blackboard lecture. Now it will be a tablet lecture, but essentially I will be writing a lot, like on the Blackboard. I only brought some slides to get you started. First with the organizational issues and also with some images so that you know what I'm thinking of when I'm talking about images, and I'm just writing some mathematical properties of them. Of course, from time to time, we will always come back to some slides to see results of the methods that we are discussing, but mostly we will be just looking at the theoretical properties. Yeah, and the first important comment is that I really like to hear questions and comments. So if there is, if any questions arises, or if you want to make some comments on the things we're doing, please don't hesitate to raise your voice and just let me know. Yeah, so I will be giving the lectures Tuesdays and Thursdays, so the time 10:30 to 12. So the rooms have changed since there are many more people signed up for the course than I expected. And actually, there are still more sign-ups than this room with this checkerboard can seat. So it is possible that we need to switch rooms again. At least since I'm using the tablet and don't need the Blackboard anymore, we are much freer in the choice of rooms because not many rooms nowadays have black or whiteboards. Good. There will be exercises given by my assistant Vera Löser, and they will start next week. So this week there will be only the 2 lectures. The exercises can only start when we have some, so enough content to do some exercises. Yeah, so as I said, next week will be the first lecture. So Moodle will be the primary source of information. I will make all announcements there with room changes or anything like that. There will be exercise sheets. So the exercise sheets are completely voluntarily. So we will not grade your exercises. So I think you're in the master and you should know by now that exercises in a math lecture are very valuable. So you will only really learn the content here if you try to solve the exercises. Yeah, but it is up to you to do so. So there would be the possibility actually to show your solutions during the exercise session if you want to. So we can discuss about your solutions. Otherwise, you will see our prepared solutions. And also in the exercises, I plan to have small attendance exercise problems. So when you when we are done discussing the exercise sheet, there will be probably like a quarter or 3/4 of an hour left where you get new but simple exercises that you're supposed to try to solve on the spot. Yeah. So I remember as students, I hated this. But now that I'm looking back, I realize that it's very valuable if you are working on new problems. And in particular, if you're together in a room, you can work in small groups on these problems. And it's very, very helpful to do this. Yeah, so that just that you are roughly prepared of how the exercises will be done. But of course, everything is voluntary, so you don't have to do this. But I hope you trust that this is worthwhile. Okay, and I'd also like to give you a brief overview of the contents that I plan to cover. So these are essentially the lecture notes have 5 chapters. So it starts very simple by precisely defining what digital images are, what they are mathematically, what the connection between the continuous and the discrete world is. And this chapter will also cover so-called point operations. Point operations are things where just one gray value is mapped to another, where you are not allowed to look in the local neighborhood, but you just have to make decisions based on the gray values. And this leads to so-called intensity transformations. And the histogram will be a very important tool there. And from there, we will move on to local operators. So local operators are where you are allowed to look at the local structure of the image to make your decisions. For instance, linear filters are typical local operator examples. And here we will look in detail at the properties of the so-called cross correlation that is based, all of this is based on. And we will also briefly look at so-called morphological operator, which are some simple nonlinear local operators that are working on sets instead of images. And after that, we will move to an important global operator, which is the Fourier transform. Yeah, so this happens in frequency domain. And this will be quite math heavy because I will introduce the Fourier transform rigorously and describe how you get a mapping from L2 to L2, so from the square integrable function to the square integrable functions. So this will involve the so-called Schwarz space. So you don't have to have heard about this before, but we will need this to properly construct what the Fourier transform actually is. Yeah, and with this knowledge, we can further move towards the discrete world with orthogonal expansions allowing approximations of functions. We will have the Fourier series and the discrete Fourier transform, of course, yeah, including the fast Fourier transform, which is very important from the numerical perspective and probably the main reason why the Fourier transform got so popular in the first place. And this chapter will conclude with showing that the discrete Fourier transform is actually solving a trigonometric interpolation problem. Then we will look at another global transform, namely the wavelet transform. While the Fourier transform is very nice, it has the problem that it's completely global, so you lose all locality going to the frequency perspective. And the wavelet transform is like something that tries to fix this, that keeps locality to some degree, but also have very nice properties like the Fourier transform. And in principle, in the last chapter, we would do PDE-based image processing, for instance, with the heat equation. But last time I gave this course, we had to stop after the wavelet transform because the semester was over. So not clear yet if the heat equation will be covered or not. And finally, I have prepared two appendices because I will need to assume that you know some mathematical background, and these appendices are supposed to collect all the definitions and the theorems that we need. So I think it's only just 8 pages, so it's not much, but it's quite dense. So later on, we will definitely need to know what the Lebesgue spaces are. Yeah, and the appendices introduce what they are and give some references where you can look at this. So just to get some basic idea, who knows what a Lebesgue space is? Only the mathematicians, probably. Yeah, so it is like a formal way to properly define what an integral is. Yeah, so there are many things that can go wrong if you naively try to integrate. And yeah, so the appendix just gives the definitions, and in principle, you can also like use it as tool. Yeah, so something to look up where you need where we need some properties. And I would suggest that as soon as we come to the point where we will really need these L2 spaces, we have a look at this together and see if you need more information on that or not. And in the meantime, I suggest everybody to browse through the appendix to see how familiar or unfamiliar it looks. And since nobody or most people didn't know the Lebesgue spaces, it will not look so familiar. But that's what the appendix is for, to prepare you so that you know what tools we will need. And yeah, I think only in chapter 2 we will really start first needing this. So the first chapter is quite basic, and yeah, probably the continuous histogram needs a little bit of this, but for the most part we will not need this yet. Okay. Yeah, I collected some references that are also in the lecture note. I think that's what I forgot to mention. So there will be detailed lecture notes. So everything that I write, essentially, so you will get also another bonus of the tablet. You will get what I write as PDF, but you will also get the full lecture notes that I'm basing this lecture on. Yeah, which is in principle self-contained plus references. And so here are just the references that I look at when preparing the lecture. So it's not that you need to read all these 5 books, but it's if you want to have more background information on some topic, it's worth opening these books and looking in there. But in principle, it's fine if you know and understand what is in the lecture notes. Okay, so are there any questions on formalities or anything before we start with some content? Yeah, so no, I did not say anything about the format of the exam because I plan for oral exams. But if really all the 70 people who are now signed up really want to take the well, oral is very adequate for the type of course because there's not really many problems where you would just compute something, and proof-based exams are difficult. But doing 70 oral exams is quite challenging for the examiners. So yeah, let's see. So I hope for oral exams, but if there are way too many people who want to take the exam, I will have to think about the written exam. Yeah, but so in any case, it's really about understanding the concepts, and so the exam will not include many or any problems where you have to compute something, but show that you've understood the underlying properties of the things we're talking about and the connections. Okay, further questions? There are no equation, no requirements. So since we are not grading the exercises, there's nothing that we require. So also, I think it doesn't make sense to force you to go to the exercises, in particular with the current situation. So I'm happy that so many people showed up here, but no, I will not force anybody to come to either lecture or exercise. So in principle, everybody can sign up who is enlisted in the course. Okay, further questions? Good. Then let's start by actually looking at some content, and I want to show you numerous examples what images are. So what you should have in mind when you think about we are working with an image. And so the most simple type of images are signals. So these are just 1D images. So we have one spatial, you can't see the mouse pointer. So we have one horizontal spatial coordinate and one vertical value coordinate. And of course, obviously, images are just also 2D pictures, either colored or grayscale. So on the left and the right, some very iconic examples that you see in many of the image processing publications. And in the middle, one example from one of our research projects from neurosurgery. You can also think about videos as images. These are just 3-dimensional images where you have 2 spatial coordinates and 1 temporal coordinate. Yeah, so the coordinates there have some different meanings and different regularities, but nevertheless, this 3D image is still an image, even if one of the coordinate axes is a temporal axis. Then there are many medical image modalities like magnetic resonance imaging, computed tomography, positron emission tomography. So these either look like usually look like 2D images, but actually these are just slices through volumetric images. So what you actually have is some 3D image stack where you can look at it, for instance, with CT. If you change the way how you're projecting things to 2D, you can, for instance, make the tissue invisible and look at the skull. Yeah, so just to illustrate that these are real 3-dimensional images, and this also falls in the category of things that we want to cover. Other modalities that are particularly relevant for my kind of research are electron microscopy. Yeah, these are in principle 2D images, but you have so high magnification rates that you can see the underlying atomic grid of the material. Yeah, so this is like a magnification of, I think, like 20 million or so, and these blobs here that you can see on the right-hand side are actually atoms. You get similar things when you look at results of simulations. So this would be like synthetic images, but still we can treat this kind of things as images. And something that is recently getting more and more important are so-called hyperspectral images. Here with electron energy loss spectroscopy being one example. So it looks like a signal, but actually you have such a signal at every single spatial position. Yeah, so it's like a data cube where one of the cubes is the one of the dimensions is the direction of your signal, which has really hundreds or thousands of channels. And in image processing, there are some recurring fundamental tasks that you want to solve and that we will touch from time to time, and that I want to briefly specify. So one very classical task, of course, is image denoising. Yeah, so you are given a noisy image f, and you can think of this as some true image f0, which is corrupted by noise. Here, an example of additive noise, and you want to recover the denoised image or the original image before the noise was added. So you want to go from the left to the right. A very classical problem. A variant of this is deblurring. If you are not being able to observe the image directly, but that the image first goes through some operator like A here, and this A would be just a linear operator, for instance, which models the blurring. Yeah, so where you put in a normal image and you get out a blurred image, and here you want to go back again from the blurred image to the the original image. Of course, this image here is not extremely realistic because the blur is applied to the entire image, and in principle you would only see blur on the plane, but that's somewhat more complicated problem to write down. Anyway, but also an interesting problem to think about. Then there's image segmentation, where the task is like to interpret your image. So you're given again an image F, but now you want to separate this into homogeneous regions that are somehow describes this image, and here the task would be to decompose into foreground and background. So the cameraman would be the foreground and the rest would be the background, and finding this separation is called image segmentation. And another problem which we only will cover briefly, but which is something that I work a lot on in my research, and that's why I want to mention it, is image registration. Here you're given 2 or more images that are showing either the same object or an equivalent object, but in a different way. And you want to bring those images into the same coordinate system. So it's always easy to motivate this with a medical example. For instance, a doctor has a PET image, which is the left one, and a CT image, which is the right one. And to make a diagnosis, so the physician wants to fuse the information, or at least have the information in a combined view. So because, for instance, in the PET on the left, you see active areas, so where oxygen is transformed. And in the CT, you see very clearly the bone structures, which are invisible in PET. So it would be very helpful to combine this. And if you just put them on top of each other, you see that this is not fitting. But I think everybody here should immediately see what one should do, namely to shift. So that the structures that show similar things are at the same position. And from the mathematical perspective, that means you want to find a mapping from the image domain, which is here just the unit square, to itself, that tells every position where to move so that these coordinate systems are aligned. And so we want that the one image composed with information resembles the other image. And this leads to very interesting questions, because how are you supposed to measure this similarity? Because the gray values, at least in this example, are very different. And also how to represent this information. And we will only briefly look at this. Okay, so this is what I wanted to show first, so that you have a basic idea of what images are and what kind of tasks are interesting. And having that set, I want to move to the first chapter and actually tell you how to describe digital images mathematically before we then start working with them. So the first chapter is called, like I already showed on the overview, it's digital images and point operators. By the way, in case there's any problem with the screen, let me know, because I will not be looking back there, and I may not notice, so I need your help. So the reference I already mentioned. And now the first thing that we will do is define digital images. And so from the mathematical perspective, an image is just a mapping. So a mapping from some domain omega So I usually call it omega, but you can usually think of it as a unit square or unit cube or wherever we are. That covers most of the cases. And the mapping goes from this domain to some value range, which I call V. And for example, we could have F, which goes from the open interval 0, 1 squared, so the open unit square, to the closed interval 0, 1. And this would be a typical continuous grayscale image. So it's continuous. And typically the convention is 0 is black, 1 is white, and everything in between is linearly interpolated. And the domain usually has a special structure, which is why we call this images. It's a d-dimensional cuboid. So it's just the generalization of a square or rectangle to arbitrary dimensions. So we have that this omega is some interval a1, b1 times an b1, not b2, a1, b1 times a2, b2, and so on. A, B, A, D, BD, which is in RD. Yeah, so the domain we're living on in images is usually very simple. And the value ranges, they depend highly on the acquisition technique, and thus there are very different choices of V available. So value range depends on the acquisition technique. And as I said above, grayscale images, there we have V equals R, or more precisely V equals 0, 1. With 0 black, 1 white. Then we have color images. Where V is either R3 or 0, 1 cubed. And actually there are very different ways how to interpret this cube. This depends on the color model. Probably one that everybody knows is RGB. So just the red, green, and blue component, which is also how typically color images are saved, exactly in these three channels. But there are many other color models available, and we will also need HSV, hue saturation value. Yeah. Yes. Yeah. If you want to see alpha as part of the image, then it would be 4-dimensional. Yeah. The transparency would be independent of the color representation. I would say you can just add it on top. Oops. No. Yes, an interesting question, because for me the alpha channel, at least if it's 0, 1, it would like actually change how the domain of the image is. Yeah, but so this is what what algorithms could take into account, but I think we will have no examples where this is actually done. Another modality that you probably have never heard about, or most of you, I'm not sure, is diffusion tensor imaging. Which is called, in short, DTI. Here V are 3x3 matrices, but not all of them, only the symmetric, positive, definite ones. Yeah, so there are actually devices that measure the image values as symmetric, positive, definite matrices. So this encodes like flow directions in the brain, for instance. Here, so this is something that we will not cover in depth, but very interesting problems arise because these matrices are not a vector space. So you can't add two such matrices and expect them still to be symmetric, positive, or subtract. Because a vector space you would also have to be able to multiply with -1, for instance, and this would be negative definite immediately. So you would actually have to interpret the value range as manifold instead of a vector space, which poses some very interesting mathematical questions, but it's also really needed in this particular example because you need to keep this structure. And last thing that I want to mention is the spectral imaging, which I already had in on the slides. So there V is Rn. or 0, 1 to the n, where the n is much, much bigger than 1. Yeah, but you can continue this list almost as long as you like. They are really very different value ranges. Just wanted to show you that there is quite a wide variety out there. So now let's really define what, for me, a digital image is. So this may look quite excessive, but you will see that it's at least very precise and gives us some solid foundation to build on, and also establish the corresponding notation. So we start with D, which is the dimension of the image that we're looking at. Or more precisely, this is the spatial dimension. And an image, or a digital image, so digital here implies that it's somehow discrete. It always has a size, which is a vector of natural numbers. Which is just like essentially the number of pixels in each coordinate direction. And I will make a picture at the in the middle of the definition, so you see how this all fits together. Yeah, and this tuple M is called image size. So, and if you combine the image size with the cuboid that I said that we have for an image, you will directly get a grid. So M and the cuboid omega together imply a grid. So how does this work? So let's take an index j. So everything underscore here are tuples or vectors. So that's how you distinguish the scalars from vectors here. So we take an index j that is in an index set I. And the indices just tell us like the number in every coordinate direction. So I said that these are the number of pixels in the coordinate direction. So in direction 1, we have m1 pixels, and we just have to take then one index between 1 and m1, and so on. So this we need to do for every coordinate direction. So and this index now corresponds to a grid node. And the grid node called is xj. So it's the node indexed by j. The coordinates I call xj1 to d. This is an omega, and I of course need to tell you what xji is. So xji. So we are essentially starting at the left side of the cuboid, and we go in direction of the right side. So this is ji minus 1/2 hi. And I will make a picture right after this so we see how these things fit together. This h is called grid size. And it's just the length of one side divided by the number of pixels in that side. Yeah, okay, so it may look very abstract, but let's try to make this makes this more clear. So I now take my cuboid that's 0.8 times 0.6. Yeah, so A1 is 0, B1 is 8, and so on. And now I specify that this, so it's two-dimensional. It is this cuboid, and I now need to say what the image size is. Yeah, that's still missing before I get my grid. And here I say the image size is 4 by 3, and what we then get is just the following separation. Okay, imagine this would be equidistant. So here we have x 1, 1. This distance here is h1. This distance is h2. Yeah, and now you can see here what's happening. We just start at one side. We go in terms of h, but only subtract then h half. That means we land exactly in the middle of these rectangles. Yeah, that's why we have the -1/2 there. Here we have x2, 1, and so on. Here the topmost is x 4, 3. Yeah, so in principle, a very simple and very regular separation of our cuboid into a grid. Yeah, so just think of this as pixels. Yeah, and the pixels are these squares or rectangles, and inside, so the center of each of these pixels are the grid nodes. Yeah, and this brings us to the term grid, the grid X, capital X. This now is a d-dimensional array. Or from a mathematical perspective, it's a tensor of order d. Or in short, a D array, where we collect all these grid nodes. So it's just all these xj for all j in our index set. And this is called a regular grid. And the special case that all the grid sizes are the same has a special name. So the special case h1 equals h2 and so on equals hd. This is a Cartesian grid. So now let's formalize these this separation here in rectangles that I already drew, but that we haven't essentially specified yet. So implied that there are pixels, but we haven't really defined them. This is what comes now. So this grid now implies a partition exactly in these rectangles. And they're not only called pixels, they're also called cells. And a cell for index j are just those omega where the distance to the central node in each coordinate direction is smaller than half the corresponding grid size. Yeah, so this Cj specifies exactly the content of the rectangle without the boundary. Yeah, so it's just the inner part of these rectangles. And it's actually a little tricky to decide which part of boundary should belong to which rectangle, but we will cover that soon when we draw the connection between continuous and digital images. So with this, we have, yeah. Yeah, so a regular, non-regular grid would be something like, for instance, where you, right. Yeah, yeah. So we will always work on regular grids, but yeah, I just added the word regular because if you look in literature, you will find exactly the term regular grid to have the connection. You decide. So it's what. Yeah, yeah. So your problem comes with a certain domain, and usually the AIs are 0 and the BIs are 1, but there are sometimes reasons why you would want a bigger or smaller. Yeah, yeah. So you need to specify both the number. Uh, oops. Yeah, you need to specify both M and A and B. Only after you have specified those two, you will get everything else. Yeah, yeah. You're welcome. Yeah, and I'm happy that you're asking. Yeah, really. If there's anything, please don't hesitate to ask. So, and now that we have formally defined these cells, let's just see some properties. So, if we unite the closure of all the cells, we get the closure of omega. Yeah, so the closure of these cells means cell plus boundary, and if you have everything together, then we have all of omega, including the boundary. So this is actually just specifying in which sense this is a partition of omega. Because if you look at the intersection of two of these cells, then it's always the empty set. So if you have two different sets. And all of them are non-empty. Yeah, and these three properties mean that they are a partition. And this grid is called cell-centered. And it's often used with finite differences. By the way, if my handwriting gets too bad, please remind me that I need to write slower. So this is used with finite differences. And in case anybody has heard about finite elements, those usually use mesh-centered grids. Or for multilinear finite elements. Mesh-centered grids are more common. And mesh-centered would mean that we don't have the nodes here in the middle of the cells, but that the nodes would be sitting here at the corners. Yeah? This here? This is the here. So the xj is the center of the cell. Yeah. So we are comparing every point in our omega to one certain cell center, and we just check that the distance is less than h half. Yeah. So first you specify j. So let's say we are here, and now you compare everything in omega to just this point, and you will realize that we only those fulfill the distance. Yeah. Yeah, maybe a little confusing. So j comes from here, and I comes from here. So this has to hold for all I for fixed j. Okay, so these mesh centers are coming there. And finally, we have almost defined now what a digital image is. So if now we assign a value to each cell, for the easiest would be a gray value. Let's call it fj. Is assigned to each cell. We can arrange these values in a D array. In a D array. Capital F. Yeah, with all these fj. Similar how we took all the positions. Yeah, here we took all the positions to form a grid. And here we take all the values. And this is now called digital image. Digital image or discrete image or pixel image. Yeah, many names for the same object. Yeah, but it's like the combination. So you not only have this tensor of values, it belongs to a grid, yeah, that you specified before, and so that you know where these values are living at which spatial positions. Yeah, so this is just an extra remark. We are looking here at cell-centered grids. Yeah, so I was just mentioning that there are other types of grids. And if you hear cell-centered, you may wonder what is not cell-centered. And this mesh-centered is just an example, but we are not looking at this case here. It's only for the sake of completeness. Okay, good. Okay, so now we have a pixel image. But there's still something that we need to discretize, because so far we only had continuous value ranges. Right, so now I have discrete positions, but still continuous values between 0, 1, for instance, for gray values. And this is now further discretized. So actual images they need a finite value range. So they are quantized. So for example, if you have a grayscale, image, and you want to store it with a precision of n bit, you have 2 to the n possible values. And for grayscale images, 8-bit is typical here. And that means that the value range is from 0 to 255. Yeah, only those integers from 0 to 255. And for color images, you usually have this 8-bit per channel. Yeah, if you make a picture with a typical smartphone and just open the JPEG in MATLAB or Python, you will have a matrix which has like or a 3-dimensional array where all the values are between 0 and 255, and this is exactly because they are quantized to 8-bit. And so this 8-bit was very, very common till recently. HDR showed up. So and those have typically a higher range. So modern video formats like HDR10 or Dolby Vision, they use 10 or 12-bit. Yeah, and so actually any non-HDR screen can only display 8-bit per channel. So even if you have an image with more than 8-bit precision, you can only view it at 8-bit per channel, unless you have a fancy HDR monitor and with proper software support. Okay, finally, let's also introduce the notion of a pixel. Because actually the pixel of an image is not only the cell, as I hinted earlier, but it also includes the value in that cell. Yeah, so this pair is called pixel. For d equals 2, or voxel for d equals 3. And pixel just means short picture element, or and voxel is the analog for volume elements. So, and finally, we can now draw the connection between this discrete image and the continuous image that we just defined as mapping from omega to r by introducing the notion of a so-called pixelated image. Two. Here? Here? After the word pix. Ach, vor. Oh, yeah. Yeah, please. Yeah. Yeah, it's really good that you ask. I have to work on my handwriting. Okay, so coming back to this connection between the continuous and the discrete images. So we now look at the function omega to v, which is a continuous image. But we additionally require that this function is constant on each cell. that means this function restricted to the cell Cj. So this means this notation means restricted to the cell. So we only evaluate on the cell. That's supposed to be constant on all the cells. This is called pixelated. Yeah, so we have now a function that's living on our omega, and it happens if we look in one cell, at every point in the cell it has the same value. Yeah, and if the function fulfills that property, then we call it pixelated. And now we have the problem of these cell boundaries. So we can look at what are we not describing when we look at omega and remove all the cells. So in our picture here, we have these internal lines. That is our L. So as a mathematician, you will say, oh, this is a null set, we don't care. So this is the Lebesgue null set. And so since the Lebesgue spaces were not so common, who knows what a Lebesgue null set is? So it's think of it as a set with volume 0. Yeah, so the in 2D, if the area of a line is 0. So it's a bit more complicated than that, but for our purposes, I think it's fine to think about it like this. It's like a one-dimensional subset of a 2D set here in this case. Yeah, so these lines are very lines are very regular, but they have no widths. That's why I have an area of 0. So and these sets are always null sets. There are more null sets, but this is one example, and then we can freely choose values there. So the values can be chosen freely. In the sense of the Lebesgue measure. So what does it mean if you haven't heard about this? So essentially, we when we want to do something with a function, we integrate over it. And if you think about, for instance, integrating a function over this rectangle, it wouldn't matter if you change the value of the function on a single line, because a line has no widths. There's no effect on the integrated value. Yeah, so that's so if you never thought about this, it's maybe hard to grasp, but this is one of the important properties of Lebesgue functions, that on these null sets you can change the value, but it doesn't change the function. Yeah, there is some theoretical background, but that can't be summed up in 2 minutes. So why this is really important to make this distinction, but yeah, these functions are changeable on these kind of null sets. Yes. No, it's yeah, okay, it's a good question. So like the problem is not that we want to change the value. So canonically now we only have the value inside, and we now have to decide what we put here. Yeah. So for the mathematicians, I'm arguing that actually it doesn't matter what we choose. That's the theoretical stuff that I mentioned. But nevertheless, I want to have a value there. And that's what I'm coming to next, to decide now which value do we consistently put there so that we have values everywhere. Yeah, so they can be chosen freely, and now I'm choosing them. And this is now, yeah, probably requires you to think at least a minute about the formula that will come before you can grasp it. So, but first, one observation. So what happens if we are on any of these lines? then we are between exactly two, or at least two cells. Yeah. So if I'm here, I'm between these four cells. If I'm here, I'm between these two cells. And like the distance, so for instance, I'm here, the distance in this direction and in this direction to the cell center is the same. Yeah. And all of these points on the lines fulfill this. Yeah, that's what I'm writing down now. So in this case, X is between at least two cells. So, and what does this mean that it's between cells? That we have some index j. Wait, I made a mistake. There is an index j in our index set and an I from 1 to d such that X is in the closure of the cell because it's sitting on the boundary. And since it's sitting on the boundary, for one coordinate axis, it has to have a distance of h½ to the center. Yeah, so going back to our example, if we are here, then we are left of that cell and have exactly 1/2 distance to the center. Yeah, and as long as we are like on these lines, there's only one cell in adjacency that's exactly fulfills these properties. But if we are here, then these three cells fulfill this property. So we are like below these two, and we are left of these two. And the idea is to choose like the cell in such a way that we are lower left, and and extending to arbitrary dimensions. So what's like this choosing lower left is what is guiding us. So if I'm here, I want to end up with that cell. And this I now formalize because I can't just say I choose lower left. So we have such an index, and now it could be that we have multiple such indices. So now comes the part to think about. We choose the index such that the number of elements in the following set is maximal. So we look at all the i's from 1 to d and check that the distance in that direction is exactly h½ to the left. Yeah, and we choose it in such a way that the number of elements in here is maximal. So let's try to digest that. Yes, please. Yes, it's arbitrary but unique. So yeah, yes. So I just want to have the values of my discrete image be fixed at every position, and so I also want to pinpoint them on these corners. That's why I'm doing this. But it's no, I did not use the assumption. Um, so these are linked but somewhat unrelated question. So it's correct that I put 0, 0 to the lower left. Yeah, so as a mathematician, for me, the origin 0, 0 is in the lower left of that we can, yeah. Here is 0, 0. This means we have a coordinate system where we are in the lower left. And yeah, you can say that I'm motivated by having the coordinate system in the lower left, the origin, that I also want like these values to be there. But it really wouldn't make a difference if I would take the upper right. Right, yeah. Mhm. Okay, so coming back to this argument that this is maximal. So let's count to see what's happening. So whenever we are not on a corner, there's only one cell that fulfills the property, so we are good. And as I said, if we are here, there are these 3 cells that fulfill the property. But from perspective of this cell, we are only up. We are not left. From perspective of this cell, we are only left. But from perspective of this cell, we are left and up. No, up and left and down. Yes. So this is like counting, and this is exactly counting that we are doing this. So this would be just 2. So this number is 2 when we are here and check this cell, and it's 1 if we have those 2, and that's why we select this. Yeah, but at the end of the day, the construction is mainly to have a unique assignment. It's not really critical how we put the values there. And just for the sake of completeness, this hash A means number of elements. And now we put these values. Yeah, f of x is f of Cj. Yeah, so that means we say that here we copy the values from that element. But in such a general way that it also works in arbitrary dimensions. Yeah, so easy to draw in 2D, but not in higher dimensions. Okay. This finally concludes this very long, but at least hopefully somewhat instructive and precise definition. Now we can see that this actually leads to very simple objects. We are coming back to this example that I drew, 2 dimensions. Omega is 0.8 times 0.6. And we have an image size of 4 by 7. So we can look at now at the grid. These are these points. Yeah, I guess it's somewhat boring. Yeah, so if we go back to the picture, so since that is 8, and we have 4 of these partitions, this h1 and h2 is just 2. So that means h half is 1. That's why we have 1, 1 here, 3, 1, 5, 1, 7, 1, and so on. Yeah, that's the only thing that this figure says. So we just have all these coordinates here, and that's our grid. And a simple image on this grid could be for example, is this f, and we just have to put some values now on each of the grid nodes. And this would be just some color gradient. It's starting with black on the left, and that's getting brighter when you go to the right. Of course, on a 4x3 image, you can't show much. Yeah, some some more remarks on the terminology. So when we have d equals to 1, we usually talk about signals rather than images. Signals and for d equal to, you usually have that these two grid sizes are the same. Yeah, so if you have 2D images, it's very rare that the pixels are not squares. And another property that you usually have more. So you usually either have that h is 1, so that bi minus ai is just mi, or h is the minimum of 1 over mi. So bi minus ai is hmi. So this is the case that your pixels have just size 1. So, and this is the case that your rectangle, that the longest side is 1. Yeah, and the others one then are smaller. So the advantage of this here, so it looks more complicated, but if you have different resolutions for the same image, that's the nice thing, is that here the domain always has size 1. Here, if the pixels have a unit size, there are some effects that change when you change the resolution. Okay, so final remark for today. Volumetric data is usually acquired slice-wise. That means you acquire one 2D slice after another, so like MRT or CRT. And the grid size in the slice is usually constant. Yeah, so that means that these individual slices are images with square pixels, but orthogonal, this is usually not the case. So that means H1 is usually not the same as H3. So these slices have a different distance than the size of the pixel. Actually, the slices are usually farther apart than the pixels themselves. So that means that the voxels are usually no cubes. Yeah, and that also can lead to strange effects if you forget that. Also, this kind of information is something that is not stored by the array itself. Yeah, if you just have the volumetric data and you just know it's a 3-dimensional array, you have no idea what the true pixel size is. This is only stored in the metadata. But this only arises when you actually practically work with these kind of data sets that you notice the difference. Okay, that is all that I wanted to tell for today, and I thank you for the attention.